I'm standing on top of the modern world, on a structure built from some of the most extraordinary materials that humans have invented.
Everything around me is man-made.
And it's built of this: sand and clay.
We've transformed sand into transparent glass. Malleable clay has metamorphosized into hard earthenware and brittle porcelain. From rock and ash, we've unleashed the power of concrete, the most widely used man-made material in the world.
I can see it's bending. It's bending quite a lot.
These miracle materials are ceramics, all forged from the stuff of the earth. And they have one thing in common: the transforming power of fire. I'm Mark Miodownik, and as a materials scientist, I've spent my life trying to unlock the secrets of matter.
Yes! It doesn't break.
This is the story of ceramics, of clay, concrete and glass, the materials we've used to make our 21st century world.
How we've taken the very stuff of the earth and transformed it into the buildings around us and the technology at our fingertips.
This is one of the lightest solids on the planet.
It's aerogel. It's 97% air. It's a glass, and it's one of the most marvellous materials we've ever created. NASA use it to collect space dust, but let me show you something else it can do. It's a fantastic insulator. The temperature under here is about 1300 degrees. But watch this. Put a flower on it, no problem at all. Absolutely fine. I can even put my finger on it. It's barely warm. Absolutely fantastic. The secret of aerogel lies in its inner structure. It's actually full of billions of air holes. It's a glass foam. And that's why it's such a great insulator and why it can absorb impacts. In the future, it might protect us against bomb blasts or insulate spacesuits on missions to Mars.
Aerogel is almost 100% air. But it's the part that isn't that's important. An almost invisible sponge-like glass foam. Glass, mainly made from sand, is a special type of ceramic. But the story of how we learned to work ceramics begins with an earthenware pot.
Clay was the first substance we learned to transform into a new material, about 29,000 years ago. And for me, that's one of the most important moments in our history. It's the moment where we learned to take the stuff of the earth, clay, soft and malleable, and using fire, transform it into something hard, immutable, a ceramic.
The first pottery figurines were found in what's now the Czech Republic. Our ancestors dug clay out of the earth. They shaped it and baked it in their fires. Much later, they made it into pots for storing grain and holding water. But they had little idea of the chemical processes they'd mastered. Magnified over 1,000 times, clay is made of thin crystalline plates which are surrounded by water. This allows the plates to slip past one another, which is why the clay can be moulded. But fire changes it forever. As clay is fired, the water evaporates. So the plates come closer together. In the intense heat, atomic bonds form between the plates and lock them into position. The clay has become hard and brittle, what later scientists would call a ceramic. pottery became one of the foundations of civilization. Although it had its weaknesses, it could be porous and would shatter easily, it would be thousands of years before we'd create anything significantly better. At least here in the West. It's 1701. A young alchemist, Johann Friedrich Böttger, is thrown into a castle dungeon by the king. Augustus the Strong imprisoned Böttger not to improve pottery, but to make gold.
This was an era in which alchemists believed they could turn base metals into gold, a tempting prospect for any king who wanted to fund their war or their court. And so Augustus ordered that Böttger be kept in prison until he revealed the secret of turning lead into gold. Picture the scene down in the dungeon, Böttger toiling in the unrelenting heat and foul air, mixing, bubbling and heating endless cocktails of ingredients. At the end of it all, he produced no gold. Desperate to keep his head on his shoulders, Böttger had to find a way to appease the king. There was one thing that Augustus valued almost as much as gold. So Böttger set out on a quest to solve an age-old mystery, and in doing so, he would change the Western world.
Böttger had set his sights on the finest ceramic then known on Earth, porcelain. The Chinese had held the secret of porcelain making for over 1,000 years. Finer, lighter, harder, whiter, with a glassy glaze. Porcelain was superior to any pottery we'd created in the West, and it was highly prized, known as white gold.
The Chinese guarded their secret closely. It provided them with a huge trade monopoly. And despite centuries of experimentation and sending spies to China, nobody in the West could discover the secret of porcelain. And this was the task that Böttger set himself to save his skin.
He needed to find out how the Chinese changed coarse earthenware into fine, strong porcelain. He started with the same basic ingredients that make earthenware pottery. So Böttger had to work out what other secret ingredients the Chinese were adding. Master potter Graham Taylor has been making porcelain for over 30 years.
He knew what not to try. People had been trying to do it for centuries. They'd tried all sorts of things to add to clay. They'd tried adding talc, powdered glass, powdered shells, things like that, all trying to achieve that sort of white translucency, that vibrancy of porcelain.
So, what did Böttger try?
Böttger had the advantage of having discovered a really, really fine type of china clay that came from Colditz. He then had to find various new things to add to that clay. There we go. So here we've got china clay, pure white clay, and in its powdered form, it looks nothing, it looks like flour.
Böttger experimented for years before finding two critical ingredients to mix with his clay.
What he's adding to it as well are china stone. This is a decomposed volcanic mineral, and quartz, about 20% quartz. So here we've got, again, another
white powder.
White powder. And here what we've got is the makings, certainly, of porcelain. Doesn't look much, does it? Of course, what we need to add to make it into a clay is some water. So I'm just going to put an amount of water in there, and we'll start to mix that up. And what you'll see happen here is we will get the paste.
But Böttger wasn't there yet. If earthenware could be forged in a blazing fire, he realised he'd have to improve his technology to make porcelain.
when they write about Botka's kilns, they talk about narrow, horizontal kilns. So I think this is the sort of shape that Botka's kilns might well have been.
By trial and error, Botka discovered he had to get his kiln to an extremely high temperature, at least 1300 degrees Celsius.
So, we'll get this burner going.
At this temperature, a different chemical process takes place. The added secret ingredients, china stone and quartz, react to form a glassy glue. This flows into the gaps between the crystalline plates. The plates begin to dissolve. Needle-like crystals form, which help lock the plates into shape. As the porcelain cools, the glassy glue solidifies around these structures and locks them into place. This makes porcelain less porous than earthenware, so it's harder and much stronger. It had taken more than a decade, but Botka was finally convinced he had something that might earn him his freedom. He decided it was time to prove his skills to the king.
Legend has it that when the king came to visit the workshop, Botka decides to open the kiln and pull out a teapot, apparently, from the kiln while it's still glowing white hot, and plunge it into a bucket of water to demonstrate the quality of the ware. And the sort of reported thing at the time is that he plunged it into water saying it must survive this test.
The thermal shock surely will just shatter it.
Well, that's what I would expect. I really am very sceptical, and I think it's an elaboration of the story and sort of building up of the story into something which it maybe wasn't. But Botka was quite a showman. He really was a showman.
Have you ever tried a test like this?
No, I haven't. Nice and quiet.
Yes, that really makes a huge difference. Got it?
Yep, up we go.
Oh, hold on. Okay.
That's it. Horizontally. And onto there.
Oh, yes.
Beautiful. Now then, what we have here is one very hot porcelain bowl that has actually fused so much. Yes, if you can tip that back into there. Lovely.
Yep.
That's got it. And what we're going to do is drop that into there. And it looks like Botka might have been right.
My God, I'm really amazed at that. I can't believe it survived. That's amazing. That is like no ceramic I've ever seen. I mean, I really can't believe that.
Well, that's me proved wrong. It survives perfectly well.
Botka had finally solved the mystery of how to make porcelain.
And he did so while locked up in a dungeon and in fear of his life. Most people would go to pieces under that sort of pressure, but Botka didn't. Instead, he pulled out of the bag one of the most wondrous pieces of material science.
King Augustus eventually released Botka in 1714, 13 years after he was first imprisoned. Following Botka's discovery, China finally lost its age-old monopoly on porcelain, and the balance of manufacturing wealth and power shifted to the West. But it took a lot less time for the West to unlock the secrets of another ceramic: glass. It was the Romans who first mastered the skills to make blown glass. They heated sand with minerals and created a toffee-like substance that they could blow, stretch and mould into any shape they wanted. And unlike any other solid they could make, it was transparent. Dr. Caroline Jackson has studied the techniques of Roman glassmakers.
The Romans were the first to use glass for windows.
Really? So
Yeah.
what happened before then?
They just had either open windows or in ceremonial places they would use other materials, but that wouldn't let the light in quite so much.
So
People must have got pretty cold before the Romans in these buildings.
Certainly was in Britain. It would have been quite drafty.
What was the process like of making this glass?
They essentially cast glass. They'd already got a casting process for vessels, so it's just an extension of that.
Like pottery, glass can be made from very simple substances, using only the power of fire. The sand, which is mainly quartz crystals, and the minerals or ash are mixed and heated together. As the temperature rises to 600 degrees Celsius and beyond, they begin to melt. The mixture becomes a molten liquid, and, like all liquids, its molecular structure is chaotic. As glass cools, its atoms bond with one another. But it can't form crystals as other ceramics would. That's because it cools too fast for its atoms to get into the regimented structure of a crystal. And this is one of the keys to its transparency.
He's taking the hot glass out of the furnace now, and he's got a wet ladle so that it doesn't stick to that, and then he's pouring it onto a very hot surface again so it doesn't stick. And he's pressing the glass down while it's very hot and molten to try and get as thin a surface as he can possibly get. The glass is cooling all the time. He's pulling out now with pincers to try and get a square shape, and you see these actually on Roman glass examples. You see the pincer marks in the corners sometimes.
In making their windows, what excited the Romans was that they could see through them.
The secret of what makes glass transparent is hidden deep within its atomic structure. Now, everything, whether it's opaque or transparent, is made of atoms. Imagine this plate is an atom in an opaque material, and this tomato is its nucleus. Well, there's also electrons inside the atom, and they inhabit things called energy levels, and they look a bit like this. Now, when a photon of light hits the atom, well, it can promote one of the electrons to a higher energy level. So it absorbs that photon of light, and so the material is opaque. So what happens when the material is transparent? Well, you've still got the atom, and you've still got the nucleus, and you've still got the electrons and their energy levels. But this time the gap between the energy levels is bigger. So when the photon of light hits the atom, it doesn't have enough energy to promote one of the electrons to a higher energy state. And so, well, nothing can happen. The light has to travel straight through, and so the material is transparent.
The Romans were justly proud of their glass-making technology. They could make more advanced shapes than anybody else. But there was one other material they invented, which would have a much greater impact on both the ancient and modern worlds. Their inspiration may have come from volcanoes, like Mount Vesuvius and Etna. When they erupt, they spew out ash, and the Romans noticed that when the ash got wet, it hardened and became almost as hard as stone. The Romans saw the potential to make a powerful new material. A material we now call concrete.
Now, I have to admit, although most people loathe concrete, I think it's one of the most amazing materials we've ever created. I love the look of it, the feel of it, and the way that it's changed the way we live our lives.
Chris Brandon has studied Roman concrete for over 20 years, and he's going to help me make some. We're using volcanic ash called pozzolana ash and adding burnt limestone made into a putty. The same ingredients the Romans would have used. How do we know that Romans made concrete this way? Is it written down somewhere, that a recipe?
Yeah, there's a recipe in Vitruvius. Pliny also wrote about it.
We're not heating our mixture, but heat is still fundamental. The Pozzolana ash was formed as minerals reacted in the extreme heat of a volcano. And the Romans heated limestone themselves. As the heat drove off carbon dioxide, it turned limestone into the very reactive burnt limestone, quicklime. We're adding water right now to make the cement paste that's the key ingredient of concrete.
We must make sure it is a stiff mix.
I can see this is a paste now, something I can mould and shape into whatever I want. The water kicks off a complex set of chemical reactions. New compounds are formed. Some are gels which harden into these fibre-like fibrils, which can be seen magnified many thousand times. The fibrils grow into a hard interlocking mesh that is the basis of concrete's strength. It's a reaction that can keep going for years, and the concrete goes on getting harder and harder. It was concrete that gave the Romans their great structures. Their amphitheatres, stadiums, and the dome of the Pantheon. Built almost 2,000 years ago, spanning a distance of more than 40 metres, the Pantheon still has the largest unreinforced concrete dome in the world. Concrete was to create not just the foundations of Rome, but of an entire empire. The Romans needed to take command of the seas.
Okay, well, here's the mini harbour that we want to build.
And to do that, they had to build harbours.
Is this going to go in just like this?
Well, I hope so.
Okay.
Drop it down.
Oh, hey.
They discovered a truly extraordinary property of their concrete. It could set even underwater.
Isn't that all just going to dissolve?
Let's wait for the water to clear.
Okay.
And what we should see is a lump of concrete or mortar
I know, I'm amazed. I thought it was just going to sort of become this...
dissolve
into this kind of mud, and then that would be it. But there it is.
And tomorrow that will be solid.
The Romans were very lucky with their raw materials. The Pozzolana ash from the nearby volcanoes had the perfect ingredients. When they were mixed together with water and burnt limestone, they produced compounds that weren't soluble. So, as soon as the chemical reactions started to form concrete's incredibly hard mesh, it wouldn't dissolve in water.
So, Chris, is this how the Romans built their harbours?
Yes, they could build out into the sea where it would have been impossible to have constructed ports with any other material. It allowed the Romans to dominate the Mediterranean.
So this is the stuff of their empire?
Absolutely, this is the foundation of empire.
You'd think with the advances the Romans made in glass and concrete technology that the scene was set for the modern era. But it didn't happen that way. With the decline of the Roman Empire, the production of glass fell away dramatically and concrete almost disappeared altogether. And it wouldn't be for another 1,000 years before those two materials were used together again. For glass, the next great breakthrough didn't come until the 15th century in Venice. And it was so significant that the Venetian glassmakers weren't allowed to leave the city or share the secrets of their art. To do so was punishable by death. Their innovation was this: Cristallo glass, the clearest glass the world had ever seen. It came from a combination of great expertise and the perfect raw materials. The Venetian glassmakers replaced ordinary sand with these clear quartz pebbles taken from the local river. They heated them up and submerged them in water to purify them, and then ground them into a fine powder. The finest sand to create the finest, clearest glass. At first, this clear glass was just used to make decorative luxuries. But then, as so many times in history, we took a material prized for its beauty and harnessed it to drive progress. Colourless glass was about to completely change the way we saw the world. Glass bends light. So if you can shape a piece of glass so that it all bends light to a focal point, well, that's what makes a lens. Light slows down as it travels from air into denser glass, and this makes light bend. As the light emerges, it speeds up and bends again. The amount it bends depends on the shape and thickness of the lens. Once you can bend light like this, you can magnify. The perfectly transparent Cristallo glass led the way to an extraordinary innovation: the telescope. It was the 17th century, and the planets had only ever been seen as pinpricks of light in the night sky. But using a telescope he built himself, the renowned physicist Galileo revealed the wonders of these distant worlds. In Galileo's day, one way to grind glass into a lens was to blow it and open it out into a sheet. When this cooled, you had to cut a small piece and then hold it against a spinning cannonball to curve it. Galileo kept improving his lenses until he managed to make a magnification of 20 times. He saw and sketched the mountains and craters on our moon. And he discovered moons orbiting Jupiter, revealing that not everything in the heavens revolved around the Earth. Our belief in a universe with Earth at its centre had come crashing down. Our worldview had been transformed by the glass lens, a simple disc of heated sand. But what's even more exciting to me is what happened when we turned the telescope around and started looking down instead of up. The irascible but brilliant English scientist Robert Hooke wanted to use the magnifying power of lenses to see what was under his very nose. He spent much of his life looking down the microscope. He described a whole new microscopic world and produced a book of astoundingly intricate drawings. Using glass lenses, Hooke had begun to unlock the secrets of life itself. He had discovered the complexity of inner space. At last, we'd be able to penetrate further into the hidden world of materials. We'd come a long way with the sand, clay and rock beneath our feet, but we were relying on materials which still had weaknesses. To build the modern world, we'd have to learn to work around their limitations. For the Victorian engineers, one challenge was concrete. It had so many advantages, but one fatal flaw. Dr. Phil Purnell has been studying concrete for over 15 years.
Well, today, Mark, we're going to get you to walk a concrete plank to give us some indication of how concrete could let us down if we're not careful.
Wow, yeah, it really is a concrete plank.
It certainly is, yes. And what we're going to do now is get you to walk across it.
Okay.
So if you'd like to sort of get onto that
I'm slightly
end.
nervous about this because I can't imagine there's a good reason for me walking a plank.
Well, as you gently inch your weight across the plank, what you're
Yeah.
doing is you're making it bend, you're bending the concrete.
Yeah.
And when you bend something, the top of it goes into crushing, it's being crushed, it goes into what we call compression,
Yeah.
whereas the bottom of it is pulled apart, it goes into what we call tension.
As the plank curves a tiny bit under my weight, the top surface becomes concave and is squashed, while the bottom surface is stretched. And of course, as I get closer to the middle, I'm making the plank work much harder.
And when you're in the middle of the plank, you have the maximum crushing on the top and the maximum pulling underneath. Concrete's very, very good. But as you can see, very, very poor in tension. And so what we've demonstrated...
That's exactly what you don't want a building to do, isn't it?
Exactly, yes. You really don't want that to happen.
Okay, wow. So this is actually a thick piece of concrete. I'm really surprised.
That's as thick as your concrete floors at home or the concrete floor in an office block. That's a genuine thickness of concrete.
Wow. The reason concrete can snap like this is down to its inner structure. Concrete isn't entirely solid. It's riddled with tiny holes. When it's compressed, the holes close up and the concrete stays strong. But when it's under tension, the holes open up. Stress will concentrate at the edges of the holes. Here, cracks can start. And the stress can be powerful enough to split the concrete. As the cracks grow, they join up with other cracks and can rip the concrete apart. So to build bigger, we'd need to find a way of working round concrete's one great weakness. So what is this trick? I mean, what is the answer to making concrete stronger, resisting these bending forces?
Well, back in the 1850s, there was a plasterer from Newcastle called Mr. Wilkinson, and he was making concrete floor slabs. And what he noticed was that these slabs had a tendency to crack in between the joists.
Just like my unfortunate experience with the plank.
Exactly like your unfortunate experience with the plank, yes. So Wilkinson noticed where the cracks were appearing in his concrete floor slabs, and he had an idea, a very bright idea. And he took some barrel hoops. He took some of the flat hoops that go around and hold a barrel together, and he placed them in the concrete where he noticed the cracks were appearing,
Right, okay.
where he knew we had to resist these pulling forces.
Right. So he invented reinforced concrete.
He did, back in 1853, yes.
What a dude.
Absolutely, he laid the foundations for modern urban life. Without reinforced concrete, nothing we see around us would exist.
Reinforced concrete might seem simple, but it works because steel is the perfect partner for concrete. They both share a surprising quality. They expand and contract at the same rate when they get hot or cold. And unlike concrete, steel is strong when it's under tension. It bends without breaking like concrete does. As we learned more about materials, we found it easier to find clever ways to fix problems. For instance, we didn't try to stop concrete cracking completely, just to control it.
So to test this beam, we're pushing down on it repeatedly with a force of about 2.5 tons. So we're putting it under the sorts of loads that we might expect, for example, a railway bridge or a road bridge to be put under when large vehicles go over the top of it.
I can see it's bending. It's bending quite a lot.
It's bending quite a lot, yes.
I hate
and
to tell you this, but when it's cracking.
it is cracking quite considerably, is it?
Yeah.
But look at the difference this time compared to our plank in the other room. Here our cracks are only travelling a certain way up because what's happening is the steel is holding the beam together. The steel is holding that crack together. If I just trace this crack out to highlight it a bit more clearly, and we can see how the crack is travelling up from the bottom of the beam, but it stops roughly halfway up the beam. So I'll just draw a dotted line there to show where it stopped. And everything above that dotted line is going into the crushing force, into compression, and everything below that dotted line is being pulled, it's going into tension. So above the line, the concrete is doing the work, below the line, the steel is doing the work. So we're getting the very best out of both materials.
So that crack is stable. I mean, nothing to worry about.
It's perfectly stable. All reinforced concrete buildings are cracked to some degree, and the important thing when designing reinforced concrete is to make sure that you have lots and lots and lots of small cracks instead of one very, very big crack.
Most people see concrete as drab, grey and ugly. It hasn't got many fans. But I think it's an extraordinary material. You can build man-made mountains with it, buildings in any shape you want, structures that will last for thousands of years. And that's the secret of concrete's success. Many of the iconic structures of our era, the Sydney Opera House, the Millau Viaduct, the tallest bridge in the world, and Dubai's Burj Khalifa, the world's tallest building, wouldn't exist without reinforced concrete. Reinforced concrete is flexible and versatile, and it's freed us from the limitations of stone and brick. In the age of concrete, the only limitation is our imagination. The Industrial Revolution didn't just give us reinforced concrete. Manufacturers finally managed to produce clear glass on a mass scale. So while concrete was giving us bigger buildings, glass was giving us this: lager. People started to drink beer out of clear glasses rather than opaque mugs. And they didn't like the dark, murky liquid they saw. So a Czech brewery hired one Josef Groll, who created a clear golden brew, far more appealing to the 19th century eye. Lager was born and became the world's most popular tipple. But while we could mass produce small bits of glass like this, we still hadn't found a way to make glass at a scale big enough to build our modern cities. It wasn't that we hadn't tried to make large sheets of glass, but they'd always had inherent weaknesses. If you make glass the traditional way, it may look perfect, but it'll always have a few flaws in it. And you probably can't even see them with the naked eye. But with a microscope like this, you can. So I'm just going to explore the inner world of glass here and have a look for some. Yeah, there's one, a little bubble. And there's another one, these little air bubbles actually. And if I refocus to look at the surface, then I can see scratches. Quite a lot of them. And any imperfections in glass could have a dramatic effect. So this is a modern pane of glass, and it has very few flaws in it. And so it's pretty strong. It's pretty impressive. Now, what if I was to put artificially some flaws in there? How would that affect the strength? Got just the tool for the job here. Let's put this back up again, and right, so now I've introduced a flaw into this piece of glass, a scratch, very thin scratch. Let's see if it affects the strength. Just as I suspected. It might seem strange that a single scratch could weaken an entire pane of glass so catastrophically. But it all comes down to the nature of ceramic materials. Any defect causes a point in the glass where the stress will concentrate. Even a small force can rip the atoms apart at the point it's most concentrated. As the atomic bonds break, the stress is focused onto the next atom, and the next, and the next. If the crack reaches a critical length, it's unstoppable. the whole pane of glass will break. Perfection is a very appealing concept, but with glass it's really a necessity. The bigger the piece of glass, the more likely it is to have a fatal flaw. And if we were going to build big with glass, we needed to find a way of making it more perfect. The breakthrough came in 1952, over a sinkful of washing up. Glass technician Alistair Pilkington was trying to achieve the glassmaker's holy grail, a sheet of perfect, flawless glass. The story goes that he was washing up the dishes and he noticed a film of washing up liquid floated on the surface of the water. He had a brainwave.
Pilkington's idea was to create sheet glass by floating it on a bed of molten metal.
It was an ambitious idea, but brilliant. And heat was once again the transforming power. Heating the metal until it was molten would keep the glass hot enough to remain liquid. And like the washing up liquid on the water, Pilkington knew that glass and metal wouldn't mix. The glass would simply float on top of the molten metal, spreading out in a puddle. And it would settle into exactly the same thickness all over, because of gravity. When it cooled, this glass should be as close to perfection as we could achieve. It took 7 years and more than £7 million to develop float glass. But the process was perfected, and it's still the way we make large sheets of glass today. But even flawless glass was still brittle and dangerous if it shattered. To use glass for our buildings in huge weight-bearing sheets, we needed a glass that was stronger and safer. A glass a bit more like this. All right, come on then. Let's do it properly. It takes a 50-kilogram weight propelled at speed to break this glass. It's up to 5 times stronger than ordinary glass. The secret again lies in the material itself and the transforming power of heat in a process called tempering. The glass is heated and expands, but then it's cooled so rapidly that the outside surfaces contract faster than the inside. This sets up forces within the glass. The middle ends up under tension, being pulled by the outside, which in turn is under compression, squeezed. This compression force holds it together strongly, so it won't break as easily. But like an explosive charge waiting to go off, once the internal stresses are released, the whole pane disintegrates almost instantaneously. And it forms not a few large cracks, but millions of smaller ones. Instead of breaking into spiky shards that can cut or even kill you, this type of glass crumbles into blunt pieces that won't do you much harm at all. But it still breaks. The search was on for a way of making even tougher glass. And once again, we turned to a combination of 2 materials with complementary properties. This piece of advanced safety glass is actually 2 layers of tempered glass, a kind of glass sandwich with a plastic filling. Plastic is flexible, so it helps the glass absorb energy from impacts without breaking. It's so tough, we can be more ambitious with glass than ever before. In theory, I should be able to jump on this.
Yes! It doesn't break. You don't have to use it for windows, you can use it for floors, for walls, staircases. It'll even withstand hurricanes. Incredible stuff. We can even make it bulletproof and bomb-proof. Unbelievable.
Toughened, laminated glass and reinforced concrete finally brought us into the age of the skyscraper and beyond. Ceramics are now shaping society in ways that are more profound than the buildings we live in. We've discovered that at the very small scale and at extreme temperatures, these materials behave in ways we just hadn't imagined. And that's propelled us into the information age. It's a story that didn't begin in a high-tech lab, but in the dentist's chair.
At the beginning of the 20th century, inventors realized that bent quartz rods could carry light. And so they created the dental illuminator.
Then, a German medical student took the idea further. He assembled lots of thin fibers into bundles to see if he could transmit not just light, but an image.
His goal was to look at the inaccessible parts of the body during surgery.
And fiber optic bundles were perfect. They could follow the contours of the body because of a surprising property of glass.
Glass at the everyday scale is brittle and stiff, but at the microscale, it behaves totally differently. It bends.
You can only see this amazing elastic property of glass in something as thin as an optical fibre, the diameter of a human hair. Atoms in glass are connected by bonds which behave a little like stiff springs. This means glass can bend a tiny bit. The finer the glass thread, the less force it needs to bend, so the less likely it is to crack. And in such a fine thread drawn from molten glass, there's less chance of a defect which could make it shatter.
That's not the only thing that's special about this glass. It's also incredibly pure.
So light can travel down it for miles. But light normally travels in straight lines, so how does it go around these bends? To find out, I'm with Dr. Natalie Wheeler, who researches optical fibres at the University of Southampton.
So here we have a length of optical fibre. As you can see, it's extremely thin, and also since it's been coated with a polymer during the fabrication process, it's also extremely strong.
Inside the coating of this optical fibre is a glass core surrounded by a glass cladding layer. It's these two layers that help the light go round bends.
We can actually demonstrate how this works using this setup here. If you would like to just pull out that cork there.
This one?
Yeah, go for it.
Whoa! Oh, that's amazing. Look at that.
This laser light mimics what happens in an optical fibre. When light travels from a dense to a less dense medium, like this liquid to air, or from the glass core to its cladding layer, what happens to the light depends on the angle at which it hits the boundary. If the angle is large enough, it won't pass through. It'll be reflected back in.
At the interface between the two materials, the light's being reflected. And you can see it bouncing along here.
So what you're saying is the interface between them allows this total internal reflection.
Exactly.
That is absolutely fantastic.
Using these amazing properties of optical fibres, in 1930, medical student Heinrich Lamm
Successfully transmitted the first image of a light bulb filament using an optical fibre bundle.
Then scientists realised they could have a far more powerful use: to transmit vast amounts of information at the speed of light. Optical fibres have become a foundation of the information revolution. Without them, we wouldn't have our world of instant phone calls, emails, cable TV, or the internet. Today, a single strand of optical fibre can transmit 2.5 million times more information than a standard copper cable. In fact, over the last 50 years, ceramics have been taking over from metals in a materials revolution that's given us our high-tech, high-speed world. Ceramics have also been replacing metals in medicine and in electronics. But there's one essential of modern life that surely metals are vital for: electricity. Electricity travels down miles and miles of metal wires to reach us. And because of the way metals conduct, some of the energy is lost along the way. If I make a small electric circuit with some copper wire, a battery and a bulb, the bulb burns pretty brightly. But now if I just use a longer wire, 65 meters of it, the same bulb, the same battery, it's much duller. So the wire absorbs quite a lot of the electricity. So when it comes to crossing countries and continents, we lose a massive amount of energy. The UK's electricity network loses more than 7% of the electricity just getting from the power station to your plug. But that could change, and it's all down to the way some materials respond to extreme temperatures. This time, the transformation isn't due to the power of heat, but of cold. In 1911, Dutch physicist Heike Kamerlingh-Onnes was testing materials at extremely low temperatures. He cooled mercury down to the temperature of liquid helium, minus 269 degrees Celsius. That's just 4 degrees above absolute zero.
Onnes discovered something that nobody had ever seen before. At these extreme temperatures, mercury conducts electricity without losing any energy at all. He called it superconductivity.
In a metal, electricity is conducted when electrons travel through it. At normal temperatures, the electrons bump into atoms and lose energy. It's called electrical resistance. But at extremely low temperatures, the electrons can pair up and navigate through the atoms without bumping into them and losing energy. The metal now has no electrical resistance. Onnes received a Nobel Prize for his work. And in the years that followed, scientists discovered that many other metals become superconductors at temperatures close to absolute zero.
With society depending more and more on electricity, superconductors seem to have a huge potential. But the breakthrough was as frustrating as it was exciting. How could we find a use for something that only worked at such extreme temperatures?
What was needed was a material that would perform like these superconducting metals, but at a temperature that wasn't down near absolute zero.
And when the breakthrough came, it wasn't a material that anybody expected to conduct electricity at all. It wasn't a metal, it was a ceramic. This is a ceramic called yttrium barium copper oxide, and not only does it not conduct electricity, it doesn't really behave very interestingly at all to electricity or magnets. It seems dead. But cold does very strange things to this material. If we cool it down, and admittedly we have to cool it down quite a lot, to liquid nitrogen temperatures, that's minus 196 degrees centigrade.
It takes a few minutes for the liquid nitrogen to cool it right down, and when it does, the ceramic becomes a superconductor. And it has another trick up its sleeve.
Now when I place the magnet over the ceramic, something completely different happens. It seems like the magnet floats on air. What's happening is it's being levitated by the ceramic. The ceramic is repelling the magnetic fields of the magnet. It's absolutely extraordinary.
The cold has changed the way the ceramic behaves. It's showing another material miracle that's unique to superconductors. Normally, this ceramic isn't affected at all by a magnet. But when the ceramic is cooled and becomes a superconductor, an external magnetic field makes electrical currents flow within it. These generate their own magnetic field, which repels the external one. And so a ceramic can repel a magnet.
This ceramic has now become a superconductor, and that means it can conduct electricity without losing any energy. It can do that when it's cooled to about minus 196 degrees centigrade. That may sound extreme, but it's pretty warm compared to the temperatures you need to make metal superconduct.
Since they discovered this, scientists have begun to design ceramics at the atomic level. They've added different elements atom by atom in search of their ultimate aim: superconductors that will work at practical temperatures.
Degree by degree, we're approaching our goal. We currently use this thick copper cable to transmit electricity, but it can now be replaced by this thin superconducting ceramic cable. And as long as it's cooled, it will lose no electricity.
In America, ceramic superconductors have started to be used in the power grid. China and Korea are planning to use them in cities of the future. In years to come, they could transport electricity on a massive scale. Just imagine, solar farms in the desert could be supplying our homes in Britain, with minimal energy being lost on the way.
Ceramics have defined our modern world. From the unlikely beginnings of sand and clay, we've created the stuff to build amazing cities full of light, and created the electronic materials that have sparked an information revolution.
Metals moved us out of the Stone Age and helped us conquer land, sea, and air. Plastics brought us the era of man-made materials and transformed our lives. Over the last century, we've designed more new materials than at any stage in human history.
And as for the future, well, I believe we've only scratched the surface of what these marvellous materials can do.
There's the first part of our fragile history of ceramics coming up tonight at 11, and that's after Silk on BBC HD Next.